Welcome back to Breaking Math, the podcast where we break down mathematics that shape our everyday world and explore the fascinating applications of technology and science. I'm your host, Autumn Finev, and today we are going to take you on a journey into one of the most precise and fundamental aspects of our modern lives, timekeeping. From atomic clocks that keep our world synchronized to revolutionary advances in optical clocks, in this episode, it promises to be both mind-expanding and practical. Time may seem like an unchanging constant, but measuring time with the utmost precision is one of the most significant challenges in modern science. Whether it's GPS signals guiding your navigation or the timestamps that keep global finance markets in order, having precise time is critical for the function of nearly every system we rely on. But how do we measure time with such accuracy, and what is the technology behind public time services like time.gov? We're thrilled to have a very special guest with us today, Andrew Novick. Andrew has worked in the Time and Frequency Division of the National Institute of Standards and Technology, or most commonly known as NIST, since 1998, where he's been at the forefront of precision timekeeping technology. He's an electrical engineer with extensive experience in working on electronics for atomic clocks and remote measurement systems, making him one of the key figures in this development and management of advanced timekeeping services. Andrew's expertise doesn't stop there. He's also responsible for managing the UTC NIST remote clock and oscillator calibration services, as well as the leading efforts on satellite timing systems and network time protocol, or NTP, measurements. Most impressively, Andrew is the creator and manager of the National Web Clock Services, time.gov, which millions of people rely on every day for accurate timekeeping. He's also authored and co-authored more than 40 papers related to time and frequency metrology, making him one of the true experts in this field. So we're excited to have Andrew with us today to discuss the cutting-edge technology behind atomic and optical clocks, as well as the real-world implications of precise timekeeping. Whether it's been from GPS systems to satellite communications, the stakes are high when it comes to keeping time accurate down to the nanosecond. And Andrew's here to help us break this all down for you. But before we dive into detail, let's start with a basic question. Why is timekeeping such a crucial part of our technological infrastructure? You might think the clock on your phone or the microwave is good enough, but when it comes to things like synchronizing global data centers, guiding spacecrafts, or testing fundamental theories in physics, precision is everything. So today we're going to explore the science and engineering that make it possible. This is where atomic clocks come into play. For decades, atomic clocks have been the standard bearers of timekeeping accuracy. These clocks work by measuring vibrations for atoms like cesium or rubidium to keep time with incredible precision. But now there's even more advanced technology on the horizon, optical clocks. These clocks promise to take more timekeeping to a whole new level, using oscillators from atoms at optical frequencies, which are far higher than those traditional atomic clocks. Now, optical clocks are not only more accurate, but they also have the potential to revolutionize the way we measure time on a fundamental level. They are so precise that they can detect minute differences in time caused by the Earth's gravitational field, a phenomenon predicted by Einstein's theory of general relativity. We'll explore even how these clocks could even help scientists uncover some new aspects of the universe, as well as how they impact the technologies we use. And of course, all of this cutting-edge technology has real-world applications, and that's where services like time.gov, the Internet Time Service, ITS, and the Time Measurement and Analysis Service, TMOS, comes in. So time.gov is a public-facing service that provides accurate time sourced from the most precise atomic clocks at NIST to your internet-enabled devices. And today, Andrew's going to give us an inside look at how time.gov works and how it's synchronized with atomic clocks and other precision timekeeping services that NIST provides us for industries and individuals alike. So whether you're a physics enthusiast, a techie, or just someone curious about how our world stays so meticulously in sync, this episode is for you. We're going to take you behind the scenes of one of the most important and yet often overlooked technologies that keep modern society ticking, literally. So let's get started and join us in this episode of Breaking Math. Hi, Andrew. How are you doing?
Hi, I'm doing great. How are you?
I'm doing wonderful. Thanks for coming on Breaking Math. Tell us a little bit about your background.
Yeah, so I'm an electrical engineer at NIST, and NIST was my student job. So I went to CU Boulder, University of Colorado, for electrical engineering, and it's just like a 3/4 of a mile from NIST. And at the time, it was National Bureau of Standards, and so I had a work-study grant. So I found a job doing electronics at NBS, and worked here all through school and eventually became NIST from NBS and eventually got hired on. And so this has been my one job in my whole career. So it's awesome.
Kind of a rare thing to hear nowadays. So consider yourself lucky with that.
Yeah, very rare. Very rare.
So what got you interested in this work? And along with that, what is time?
Yeah, so I mean, it's interesting because I came here in like junior high for a tour. And so maybe I knew a little bit about NIST, but really what got me interested was working here. You know, I was working here, we're doing the work study, and I learned all about, time and frequency measurements and calibrations and metrology and standards. And so it was really just being here is how I got interested and how I've stayed interested all this time, because it is just a really fascinating subject. And the subject of time, I mean, we're kind of lucky with time because it's something that a lot of people understand to some degree. Like if you talk about like the kilogram or the meter, how you measure a meter, like you lose people pretty quickly. But time affects people's lives all over the place. And really, at least time of day or the duration of how long it takes for something to happen. And something like, say, speed of light, right? Like people are kind of confounded by that, like, speed of light. But it's also something they can kind of grasp it. And so it's in our common vernacular. So I feel like time, we're pretty lucky. And, if you want to think of it, like if you want to define time as physics, you have the 3 dimensions and then you have time. You could debate whether you want to call it a dimension or not, the 4th dimension. But without time, like none of these things in physics work. Like, you drop something and like, how long does it take? Or you want to talk about mass or velocity. All of these things have a time component. So I feel like we're pretty lucky, but also time is pretty relative. At least how we perceive time. I mean, what we do at NIST is we define time, a very specific duration that's not relative, doesn't change, but how people perceive of time. Like, oh, wow, that 20 minutes went by really fast. Or, well, this last 5 years, like, was really fast. Or like, man, this, I have a test on Friday and there's no time to do it. Like time either goes fast or slow, depending on what you're doing, what you're perceiving. And so those things are relative, which is cool. I mean, if you want to talk about time dilation and relativity, time is also relative in physics, but that's a whole separate discussion.
Absolutely. So to kick things off, really, could you provide an overview of what time.gov and Internet Time Service and the roles they play in delivering precise time to the public?
Sure. We have here what we call the time scale. So NIST time scale, and that's a bunch of atomic clocks, which I'm sure we'll talk about later. But we define the duration of 1 second for America. So we're the federal lab that defines the second. And then we define what the time of day is. And we're also the resource or the reference for frequency. So with this time scale is a bunch of atomic clocks all averaged together. And we could talk about time scales all day, but let's assume for a minute that we know exactly what time it is, and we can define the second, and we can define frequency. So how do we get that out to the world? One of the biggest ways we do that is time.gov. So it's our federal government web clock. And the other way is NTP, Network Time Protocol. So that's our internet time service. And these are both free. They're called services, but they're free. And time.gov, basically, from any browser, from any device, you go to www.time.gov, and that browser sends a request packet to our server. And our server is on time, right? It's linked to our time scale. And so we get this exact time packet and we send it back to that browser, and here's your time, right? Except for, we know about latency, right? There's latency in that. So it took a while for that request to get to our server, and it took a while for that exact time packet to get back. And that latency can be milliseconds or hundreds of milliseconds. And so like 1,000 milliseconds is a second. So if we're already at 100 milliseconds, like you're coming up on like something that actually could matter. So what we do is we use whatever the local oscillator, say in your phone or in your computer. And when you send that request, it actually makes a timestamp from that oscillator, like your computer clock or your phone's clock, to microseconds. So like, a lot smaller designation of a fraction of a second. And then the network transfer goes to our server, comes back. And then when you get those time packets back, you look at that clock again and you say, 342.009 milliseconds transpired in that round trip. And so we don't know how long it took for the packet to get to our server versus how long it came to get back, but we know that round trip. So if we can estimate or assume that half of the round trip was there and half the round trip was back, which is probably never going to be exactly half, but we can estimate that, and we can have a pretty good way of taking out that delay from when our server set the packets to when it gets to the user. And in the case of time.gov, it doesn't totally matter because it's really just a visual clock that's running. So you can see this clock. You're not really using it to measure something. You're really just getting a visual clock. And then we do have different time zones. And so those things change sometimes. Time zone rules or time zone borders change. So we have a map that shows you, and you can look at the time in different time zones. So NTP actually sets a clock. And so there's nothing visual about NTP. You can actually run it from a command line. Or you can write a program that in the background goes, but it does the exact same thing. It goes to a NIST server, gets a time packet, comes back, uses that round trip delay, takes out the half the delay as the estimate. And NTP is, it's a software clock. You get these packets back as numbers. And the good thing about that is you can set a clock with it. So if you're running it on a device, say a computer or a stock market timestamper thing, or even like a punch clock, like at your job where you're like clocking in. I don't know if people do that anymore, but it's probably
There's
somewhere.
quite a few places that I know that still do.
Yeah. And it might be a software, you're clocking. So you want to make sure your computer's right. So NTP can set a clock, but because of the network latency in that estimate, we don't really know exactly, but it is on the order of milliseconds, probably single digit milliseconds. And with time.gov, we get about 20 million hits a day during the week. It's less on the weekends. I guess people are less on their devices on the weekends, which is kind of nice. And then NTP, our internet time service, is over 100 billion per day.
Wow.
So it's like, I don't even know how many computers there are in the world, but it's probably less than that. So there's computers that are checking quite often, especially server computers that want to keep very close. They set themselves like multiple times a day, maybe multiple times an hour.
Absolutely. Now, could you explain to us why precise time is so critical in everyday activities and how these network time services ensure this level of accuracy for us?
Yeah, so it's questionable, like how, something like time.gov or like your cell phone clock or whatever, it's going to ensure that you get to the meeting on time, or you're late, but you're late because you can see what time it is.
Yes.
It used to be that people would set their alarm clock by like 7 minutes ahead or 9 minutes ahead so that their alarm goes off and they trick themselves into thinking that they're late so they get up. But nowadays, like a lot of clocks are set automatically, so you really can't do that now. You have to get like an analog clock to trick yourself. But most people's like cell phones, you can't set your clock ahead. You can't really trick yourself now. But NTP is used. I mean, it's synchronizing networks, it's synchronizing computers, it's synchronizing data. So data transfer is a huge thing. I mean, what do we do all day, right? We're on the internet. We're on our phones, phone calls. We're listening to something, internet radio. So those things need to be synchronized, at least milliseconds, if not microseconds. So synchronization is important for time stamping, for just communications or power grids or things, sending either data signals or power signals. You have to synchronize both sides so that they don't, cross paths the wrong way.
Yeah.
So synchronization gets more and more important. And especially with the amount of bandwidth that we shove through the airwaves and the internet waves now, we're trying to put so much information through. The better synchronization and the better time you have on both sides of that synchronization, the more bandwidth you can do. So I'd say on these kind of levels, milliseconds, microseconds, that's the kind of things that you're seeing. Other things, stock market transactions is a big one. High-speed trading, they really want nanoseconds. So let me know when you're ready to talk about nanoseconds. But right now, NTP is this microsecond timing, and it's most of the clocks. Most of the clocks that is not just time of day to get to a meeting, but something better than that is probably synchronized through a network.
Definitely. Now, if we're going to dive a little bit deeper into how we're looking at networks and how even NIST synchronizes its devices to atomic clocks, can you explain that for us a little bit and how that process works?
Yeah, so an atomic clock is, if you want to delve into that,
Yes.
atomic
Please.
clocks use the naturally occurring frequency from atoms. That's what makes it atomic. We're using frequency, so it's called resonance frequency. And so all atoms have different properties of their orbital levels and energy levels. So if you think back to chemistry class, you have an atom, we have a nucleus, and you have these orbitals, right? And there's electrons on those outer layers of orbitals. And so when I say different atoms have different resonant frequencies, a resonant frequency is something that happens when an electron jumps from one level to the other. And so if an atom goes into a lower energy state, like it decays into a lower energy state, we're not talking about like nuclear or like radioactive decay, but just an atom is decaying into a lower energy state, it might give off a photon because that energy goes somewhere, right?
Yes.
And so when an atom changes states, that's significant, and it's related to frequency, either that photon, or if we can hit an atom with a right frequency, that it's resonant frequency for that particular state of atom, we can actually make that electron jump to a different orbital. Or there's a spin state. There's an orbital spin state of an electron, and a frequency can make that spin go from one way to the other way. So there's all these different properties of atoms, and it's related to frequency. So it's an energy level and spin relationship with frequency. So that means we have this really valuable thing that frequency can be used as a naturally occurring frequency. If you have a cesium atom of a certain state, and I have a cesium atom in that same state, and we hit it with a frequency to make it change to another state, and we do that from one state to the same other state, you and I have the same frequency. So we can somewhat synchronize frequency without ever comparing or being in the same place. And so atomic clocks exploit this fact, this natural frequency that you can get in or out of atoms. And we actually use it as we generate a frequency and we hit atoms with a frequency. And did they change state? We move that frequency back and forth until we get that peak of where the most atoms change state. And we lock onto that. And we just keep generating a frequency and keep steering it till we get the most state changes. And that, how that moves and how that steer goes back and forth, that's really the stability. So we just kind of try to fine tune it. And so if you turn off, if you get the right frequency, okay, we're on, we got the right frequency. If you turn off the atoms, then that frequency will be drifting. So you're constantly adjusting the frequency. It has to be on all the time because you're generating that frequency from, in a lot of atomic clocks, you're generating from a quartz crystal still. So we lock to frequencies, a naturally occurring thing from atoms. And so you have an atomic clock. And the second is defined by cesium. So cesium atomic clocks, so there's a very particular 9 gigahertz frequency that will make cesium atoms change from the F3 to the F state. And not that those states matter, except for pointing out that there's very specific state change that you're looking for. And so 2 atomic clocks that use a cesium atom are going to be very close to each other in frequency. And so there's rubidium, and that's a different frequency. Rubidium atoms will change with a different frequency. And those, it's a little easier, a little cheaper, a little bit less power. So you can buy a rubidium oscillator for maybe $1,000 or $2,000 or $3,000, whereas a cesium oscillator is going to cost, upwards of, $80,000 or $100,000. So much different. So not everyone can afford the cesium, which is why you have the rubidiums. It just depends on what you need and how often are you going to steer it or synchronize it. But once you have like the best, and really to get better than a cesium, you can get a bunch of cesiums, right? And you average them together. And so then any of the instabilities might average out or cancel each other out. And so when I mentioned the time scale earlier, that's a bunch of atomic clocks, and they're averaged together in a weighted average. So your math, right? A weighted average is a statistical average. And so in this case, what we do is the clocks that are closest to the average get the most mathematical weight. And so that way, if a clock starts drifting off, say it's some temperature thermal runaway, or it's running out of cesium, it's getting worse somehow, or some components are failing. As it gets away from the average, it gets less mathematical weight. So it's not pulling the whole average with it. And so that's what a time scale is. So we have a bunch of atomic clocks, and different countries around the world have multiple atomic clocks in their time scale. And we all contribute our clock data to the Bureau of International Measurements, the BIPM, in France. It's an international territory within France. And they're the international metrology lab that takes all the data in for all the standards. So we all contribute clock data, and then they take the hundreds of clocks around the world, and they do a weighted average, and they come up with UTC, the Coordinated Universal Time. Then they publish a document called the Circular T that says, okay, we came up with the average. It was a while back, but what we did, we came up with this average, and here's how close your lab or your clocks were to that average. And so everyone can kind of gauge or steer to the international average. So we just get better and better over time. But I do want to point out something. When I was talking about atomic clocks and frequencies from atoms, I wasn't mentioning time at all. That was frequency. So atomic clocks are not really clocks. They are, sorry to burst the bubble on that, but
Tell us more.
Atomic clocks are oscillators. They're getting their frequency locked to resonance frequencies. So if I have a cesium oscillator, it's running at 5 megahertz or 10 megahertz output. It's very, very, very stable. That's a very well-defined 10 megahertz, right? But 10 megahertz is not time, it's frequency. Frequency is 1 over time. So that's 10 million cycles per second, 10 megahertz, right? So that's cycles. A cycle is a sine wave. That sine wave can be anywhere in phase, right?
And it's perpetually oscillating.
Yeah, it's perpetually oscillating. And so it's very stable, but we have to decide what's on time. Like when that zero crossing happens, you could mark that and then you count 10 million later, 10 million cycles later, and then you have 1 second. So now you've converted by dividing down, you've divided down this 10 megahertz by 10 million. And now you have 1 cycle per second, which is 1 second. And so when I explain like what clocks and how we tell time to anybody of any age, young or old, I define a clock as something periodic and something that's counting. And so if you think about like the really early clocks, like the sun, right? You could count a day because every time the sun is directly overhead, and then 24 hours later, the sun's directly overhead, like that's a day, right? And the sun is periodic. It's not human controlled. It's just happening over and over again. And so you count it. And you can break down that sun going overhead with a sundial, right? Where you're taking that one day thing and you're using a shadow and some demarcations to break it down to smaller amounts. If you have a grandfather clock is another good example. That's a mechanical human-made thing. So the period of the oscillations is based on the length of the arm. And so you can tune it by changing the length of that arm, but it's going to swing back and forth. And so that's your oscillator. And it's not perpetual oscillation, right? You have some kind of a weight or a spring that you've pulled to add a little bit of energy to that arm each time so that it keeps swinging. But the rate of which it swings is based on the length of the arm. So you can calibrate that. But then you got to count it, right? So someone can be there like 1, 2, 3, 59, 1 minute, 58, 59, 2 minutes, right? But that kind of a clock, a pendulum clock or a grandfather clock, there's gears in there, right? So every time that goes back and forth, another gear turns in the same direction. And so that gear is the seconds. And then there's a different gear on that once that 60 teeth of that gear goes around, then that one clicks once. That's the minute, right?
Yep.
And then that one has 60 teeth, or however, it might be more smooth than that and not just go every minute. But there's gears for the minute hand, gears for the hour hand. And so that kind of a clock is something periodic, the swinging of the arm, and the counter, which is the gears. In the case of a quartz crystal, early 1900s, quartz crystals, we found that this piezoelectric quality of quartz, where you can take a thin sliver of quartz and bend it, and it actually gives off a voltage. Or if you have a thin sliver of quartz and you give it a voltage, then it will bend. And so you can use this by making an electronic circuit that makes some piece of quartz bend. Then when it bends back, it gives off a voltage. You feed that back into itself and it makes it bend again, and then it unbends. And so you can create this oscillation by this bending back and forth. And properties of the electronic circuit and the properties of the quartz and how it was cut and the shape and the size can dictate that frequency. So you can actually tune that oscillator. And so there again, a quartz watch or a quartz oscillator is just the oscillator part. And then you have to count it. And so you have some 32,768 hertz oscillator inside your wristwatch. And you have to count that down by 32,768 to get to 1 second. Do you know what the magic of that number is, 32,768?
No. Tell me.
It's 2 to the 7th. So in early digital electronics, it's very easy to divide by 2, right? So if you have 32,768 and you just send it through where a sine wave, you count every other cycle. Now you have a frequency at half. And then you count that every other cycle, or like a digital electronics, maybe it's just measuring pulses. And it says like, okay, just look at every other pulse. And you can look at every other pulse and divide it by 2. And so you divide by 2, divide by 2, divide by 2, divide by 2, and then you get to 1 second. And so because a quartz crystal, there's no quartz crystal that won't run that slowly at 1 second. That would be, it has to be in this kind of self-oscillation. So you have to get a higher frequency. And really, the higher frequency, the better. So if you had like a 10 gigahertz quartz crystal, then you divide it by 10 million. And if it's stable at 10 megahertz, you're dividing down that stability. And so you could, if you're very stable at 10 megahertz, you're much even more stable at 1 hertz. And so the higher frequency, the better. So the benefit of like atomic clocks, they might be at a gigahertz or 9 gigahertz in the case of cesium. So you're really stable at 9 gigahertz. When you divide that down to a second, that clock will not be off by a second in millions of years. And so you have this huge advantage of higher frequencies, and you're stable at a high frequency, and you divide that down to a low frequency to get your time of day or your seconds. I think, what was the original question? Did I answer it?
I
You're talking
think
about
you
how do you get
did.
time from
I
atomic
think you
clocks?
did. And as you're talking about that, I just had the floating thought of, we talk about time. Everyone talks about crystals, crystal vibrations. And I just had the silly little joke in my head. Is it time? Is it magic? Or is it witchcraft?
Yeah. We have a big quartz crystal in our lobby.
Yep.
That's like a big natural quartz crystal. It's really cool. And so when I tell people how quartz, how quartz clocks work, I talk about this crystal. And I talk about, because a lot of people have heard about like the magic
The magic of
qualities,
time.
magic of quartz. The
Right.
quartz has vibration. So if someone's holding it and they're feeling the vibrations, and then it's kind of magic. And like, I don't have much to say about that kind of magic or witchcraft side of it, but it's true that quartz does have this really interesting, maybe magic quality of this piezoelectric, which is physical, right? It's not magic, it's physics. But the fact that if you take a rock or this crystal and bend it and it gives off a voltage, it really is storing some energy in some way. And if it bends back, if you bend it and it gives off a voltage, and then if you give it a voltage and it bends, I mean, that's a pretty cool property. Call it what you will, but it's pretty neat.
So precise timekeeping impacts many different sectors. So how do industries such as telecommunications, financial services, and IT rely on NIST for their operations? And can you provide some examples of how these critical systems or services depend on accuracy of time by the services that are provided by NIST?
Yeah, so it's a little hard to explain like something like the power grid, but power grid is time and frequency, right? You're sending off voltage in a three-phase power down the lines, and then you're combining those back for some voltage at 60 hertz, for instance. Like what you plug something in the wall, that's 60 hertz.
Right.
But from power station to power station, they're exchanging energy back and forth with each other. So they have to be in phase. So the one way is if they have some way to see the phase coming in and match that, right? But two different sides coming in, it's handy or helpful if they are in phase to begin with. So then when you're sending power back and forth and it's already in phase. So how you do that is you have to synchronize the stations to each other so that when they send power back and forth, they're in phase when they get there. So power grid's a great example. I mentioned a little bit about internet, and stock market is a good example of, you have millions, maybe billions of transactions happening at a time, like every second. You say a billion in a second. And so which one came first, right? If you don't have an accurate clock, you say, okay, well, a billion happened in this second. And, it used to be, I think 7 or 8 seconds. So all the timestamps on stock transactions, in movies where they're like passing back and forth, like pieces of paper, and they're buying, selling, the time stamps were something like 7 seconds. So it means every trade that happened within 7 seconds happened at the same time. And then it went down. So who gets to decide? Whoever's like stacking up those papers, oh, I'm going to put this one first and then this one or whatever. Or then it was down to 1 second. Right now, the United States stock market designation for timestamps is 50 milliseconds. And that's huge, right? You're still having like almost a billion transactions happen in there.
Right.
So somebody,
just one teeny tiny click, two people clicking at the same time is not the same time.
So you need to decide, because if someone bought it and the other one person sold it, or if you sold a lot of them, the price is going to maybe go down, or depending on if there's offers, price is going to go up. And so every trade changes the price. So you really have to tell who got in their trade first and second and third, because the price is changing between those. So high-speed traders can exploit this fact, because they say, I see a trade that's happening and I'm going to get in on that before that trade because they're faster or they're seeing something or they see something, they're reacting faster because they have better clocks or better synchronization. And so I'm not sure if they need nanoseconds, but in the markets and the high-speed trading, they want nanoseconds. So whether or not they can use nanoseconds or tens of nanoseconds, they all want it. They want to be as close as they can so the latency is small, and they want to have exact synchronization so that they can plan ahead by microseconds or nanoseconds. And so we have basically NIST steered clocks and time services inside of data centers all over the world. And at first you're thinking, wait, you're just helping the high-speed traders, are you? Like, great, thanks a lot, NIST. But what happens is if we're in the data center and people are synchronizing and someone wants an advantage by being within 10 nanoseconds, but then the other person gets that same advantage because they're getting the same service. Now you've equalized them. They both have the advantage, which means no one has the advantage.
Right.
And so what we've essentially done is we've made the stock market accountable because now you have a lot better clocks and a lot better, you can time those transactions better, even though the legal limit is still 50 milliseconds, but people are doing it a lot faster. And so you're helping order those transactions and cut down on those advantages by homogenizing the advantage. And so this has become very popular. So we're in lots of data centers. NPL, the national lab in England, has services for their data centers too. And in Europe, it's 100 microseconds. So it's a more stringent rule than here, but it's 100 microseconds to UTC. So in America, the stock market rule is 50 milliseconds to NIST. So we're part of that legal traceability. In Europe, it's 100 microseconds to UTC, which means if we have our system at a data center in London, people can use UTC NIST to get to UTC, just like they could use NPL to get to UTC. So we have this advantage that you're able to use UTC NIST in any data centers, pretty much, I think, around the world because we have them in a lot of places. Whereas in America, you couldn't really use NPL because the legal traceability is to NIST.
Now, tell me a little bit more about how this works also for power grids and internet services.
Yeah, so power grids, I don't think I could explain any better with power grids except for they need to be in phase. If you had two, say 60 hertz signals coming in, just as an example, I mean, three-phase power is all different, and you try to just put those in the same wire, if they're not in phase, they're going to explode or they're going to cause power going back the other way. Just being in phase to some degree better than what microsecond time synchronization could do for that phase determination is good enough. I think it's something like 10 or 12 microseconds in time to keep that phase in for power grids. Internet is more about, you send a JPEG somewhere in an email, right? It's all ones and zeros. Everyone says ones and zeros. Here's where it actually becomes ones and zeros because that JPEG is data. And it's not just ones and zeros. It's a bunch of ASCII characters all encoded and compressed. And you send that, and some of the data might go, from you to Chicago to California. Some of the data might go from you to Florida to California. They're just picking whatever's the fastest way to get packets through. And so that all of those packets from that one JPEG are not going the same route. But when they get to where they're going, it's getting all these packets in. The catchers, they are catching with this catcher's mitt, and you're catching all these packets in. Like some are coming from here, some coming from there. But you need to put all these packets back together. And so in that sense, the timing is not that critical, except for if you're the catcher and you're catching millions of packets from all over, you need to have a good oscillator to be able to just accept those packets or send those packets. And so the more stable the oscillator, the more bandwidth you can handle. And so it's very hard to explain. One other sector that I wanted to talk about, because you were saying, what sectors are important. GPS is kind of ubiquitous, right? Global positioning service or global positioning satellites. service. And so the only way that GPS works is because of atomic clocks. So let's explain that a little bit because it's fascinating.
Yes, please.
So if a satellite's sending a signal to you and it says, hey, here's where I am, its position in the orbit, semi-hemispheric orbit, it's sending you a signal that says, hey, here's what time it is, here's where I am. And you get that information, you're like, okay, great. Here's what time it was when they sent it, not what time it was when I received it. Same as problem with that time.gov problem, right? It sends it, but there's some latency to when you get it, right? And the satellite says where it is, and then a second later it says, here's another signal of what time it is and where I am, but now I'm over here. Because it's moving in orbit, right? So you're getting all these packets from a satellite, where it is and what time it is, and lots of other stuff, but break it down into that. So if you know roughly where you are on the globe, you could say, okay, well, I got this, and the satellite told me where it is, and so I might know kind of where I am already. So if it took, and I might know kind of what time it is, right? So, or you could say, okay, well, the first satellite that comes in, I'm just going to synchronize to that, even though I know it's late, but I'm going to synchronize. But then I get a signal from another satellite at the same time, or almost the same time, and it's much farther away. So you get that pulse a little bit later from the one that's farther away, even though both satellites sent them at the same time, but one of them you got quicker than the other one because you're closer to that. So imagine, they say about triangulation.
I was just going to say that.
Yeah. So if someone yells and three people hear it, or three people yell and one person hears it, and you hear it slightly different, you start to say, oh, I'm closer to that person and farther from that person, and this person's about in the middle. So you can start walking towards the closest one, or walking towards the farthest one and see if the closer one gets farther or not, because it's a triangle. So you could get to some point in that triangle where they all get to, the sound all gets to you at the same time. So now if you know where those people are, now you know where you are because you've kind of centered yourself amongst the three signals. So imagine if you have 8 of those signals, or 12 of those signals, or 100 of those signals, however many satellites you can see, and they're all sending information, and they're all synchronized to within nanoseconds or a nanosecond to each other. And that's a whole different part of that. But for now, let's just assume that they all are synchronized to each other, and they're all sending you signals, but you're getting those at slightly different times. So you know where they are, and you know how long relatively they took. So you can start to figure out your position and your time. And the more satellites you have in view, the quicker and better position you can get. And so the only way that works is because it's radio propagation, which through free space, or not really totally free space, but free space, so that's roughly the same from one satellite to you as the other satellite to you. And they're synchronized. And so you're getting the signals at different times, which means you know your relative distance between you and all those satellites, and you know where they are, so you can start to average into where you are. When I say free space, not really. Like, they're all going through the ionosphere, the troposphere, the magnetosphere, right? So the signals actually get refracted through there, and they don't come exactly at the same rate because of that refraction. So, or if there's a solar storm, we've had a lot of solar storms in the last year, and that actually affects the signals of GPS or other satellites coming through that magnetosphere. And so GPS is noisier during a high solar magnetic period. And so, but nevertheless, because of atomic clocks and because of radio propagation from a satellite to you, it's pretty amazing. You could almost call it magic. It's incredible how you could determine your time within nanoseconds, and also your position within, meters or even centimeters with the right kind of math around it.
So simply put, these frequencies will actually affect the GPS systems and deep space navigation.
Yeah. So the deep space navigation and VLBI, very long baseline interferometry, those things, you need to be very well synchronized in time and frequency, Because if you're off in frequency, you're not going to communicate with that very distant
Right.
ship or transmitter. And so you need to have very accurate and stable oscillators and synchronization to communicate in, like you're saying, deep space.
Okay. So, from a purely theoretical perspective, what impact would these clocks have on fundamental physics, especially when testing Einstein's theory of relativity?
Yeah, it's amazing. A lot of things that Einstein did are amazing, but like
Right.
something like this, like, I mean, how did Einstein know like the subparticles of atoms without being able to observe them? How did he know like time dilation? I mean, it's wild that he came up with that, but he did. And eventually clocks caught up to that, where it's like, okay, now we have cesium-based atomic clocks, and we're going to accelerate. So you synchronize two clocks and you accelerate one, put it on the Concorde jet in the 80s, and you're going to leave the other one, and you're going to fly around the world or something, and then you're going to decelerate back, and you're going to compare those clocks. And those clocks, because of the velocity, the g-force, and the relative motion of one clock to the other, one clock was slower than the other for that period. And so you're like, wow, we can actually measure it now at the atomic clocks. But fast forward to modern times, in the last 10 or 15 years, with optical atomic clocks, we've got to the point where even the relativity of a clock just based on gravity, we can measure, because the atomic clocks are so good now with the optical atomic clocks. So in other words, if you have some frequency on a laser table with an optical clock, and you change the height of that laser table by several centimeters, that frequency, that relative frequency changes based on its effects due to gravity. And so you're talking about measuring very minute changes of clocks themselves, relativity, using atomic clocks, with just by moving it by 10 centimeters or something.
Okay. So let's take half a step back here, because you switch to optical clocks. Now let's explore these mechanics a little bit. And how do I believe it's optical lattice clocks work, and what makes them more accurate than some of these previous generations of the atomic clocks?
Yeah. So remember I said earlier that the higher the frequency, the better. Right? So an atomic clock's better than a coarse oscillator at 10 megahertz, because you're at this high frequency and you're stable at this high frequency.
Absolutely.
So those kind of atomic clocks, like cesium, rubidium, those are microwave clocks. Just like your microwave oven, it's microwave frequencies. So 9 gigahertz is within that. That's the cesium frequency. So optical clocks are based on atomic transitions that happen in an optical field, like a laser. So instead of hitting an atom with a certain frequency and making it change states, you're hitting it with also a frequency, but a light frequency. And so now your frequency is not derived from quartz crystals multiplied up to 9 gigahertz. It's derived from locked lasers at very high frequencies. And those atomic transitions are like in the terahertz. So now you're locking to atomic transitions at very, very, very high frequencies. So when you divide that down that instability, it's incredibly better. So like if a cesium clock is good to parts in 10 to the 14th, so that means you have some frequency with 14 decimal places of 14 zeros or whatever, like 1 hertz at 14 zeros, or 10 megahertz at several zeros, right? When you're talking about, so we say like parts in 10 to the 14th, or 10, 5 times 10 to the minus 14th. Same thing, different kind of nomenclature. The optical clocks are stable at like parts in 10 to the 17th or 18th. So many many magnitudes better. And so because it's higher frequency, because you can determine optical, it's a higher frequency. So every zero crossing is, much closer together. So it's just a much more fine tuning with those high frequencies, and you can lock in those optical frequencies so much better. Optical lattice clock is, so if you just say you have one atom and you hit it with a frequency and you change the state. So, okay, we know, okay, their frequency is good, but you need a bunch of atoms, right? And so with ion clocks, they would take ions and put them in an electromagnetic field. So they line up charged particles because it's electromagnetic. They use charged particles, and they can line those up with like putting forces in all directions. So you have a line. And then with a fine tune kind of frequency, you can hit one atom with the frequency and make it change states where the other ones didn't. Or you go over and change another atom and change that frequency. So you're starting to have this quantum based, so atomic states, subatomic particle, charged particle ion clocks. You're able to change one and not the other. And so you could really make a logic gate out of that. Like you're talking about ones and zeros. Did this change state or not? Is it in one of two states, one of three states? And so if you can control atoms, and you probably know where I'm going with this, but quantum computing, right?
Of course.
So some of our work, just all we're trying to do is make better clocks, right? So we're lining up atoms, we're turning on one atom and not the other. Because, in a cesium clock, you just got a bunch of atoms kind of streaming past, and you're hitting them with the frequency, and you see how many change state on the other side. So that's kind of like the shotgun approach. Whereas
right,
the ion clocks, you're actually taking ions, putting them in a row, and how fine tuned can you just change one and not the other? So you're not like just blasting them all because they'll all change states. So you didn't really learn anything there. So if you have an optical clock and you have to line up these atoms, you would really have them in a line, right? But that's not efficient, because if you wanted to have 1 billion atoms or 100 billion atoms or whatever, that's really getting to be a longer line. I mean, 100 billion atoms is not that long of a line, but the more atoms you have, it's a long line. So optical lattice says, okay, let's not put them in a line. Let's put them in a grid, like a checkerboard. So you have atoms in every square in the checkerboard. So now you don't have to have this really long line. You have this grid that's getting exponentially bigger by, if you just go out one more checkerboard grid, like a 5x5 grid has 25, right? If you just go one more level out, that's a 6x6 grid, you have 36. So an optical lattice is basically just putting those atoms in a well, and you're spreading them out that way. And so you can interrogate those atoms with different frequencies and have in more data, basically more bandwidth, more data. It's all about getting more bandwidth, right? You have more atoms, but in this case, you can control them independently. And so that's where that lattice part comes in. It's the checkerboard of atoms instead of like a long tube of atoms.
Now, you touched base a little bit on quantum computing. Not to foreshadow another episode that we're going to have in the next few weeks this season, but what advancements do researchers hope to achieve with optical clocks even over the next decade? And how could these advances open doors for new scientific discoveries or even drive new emerging technologies?
Yeah, so we have this odd thing at NIST, and we're creating technologies or abilities with not really a total goal in mind. In other words, we're like, if we had better clocks, what could we do? Like, I have no idea. And then, like GPS comes out. We're like, oh, see, they figured we came up with these really good clocks starting in the 60s, right. The atomic clocks. GPS didn't come out till the late 70s or early 80s. So the atomic clock development wasn't because someone had an idea, I think, for GPS. It was like, let's just figure out how to make better clocks. Who knows what we need them for, right? But somebody will, once we come up with it, someone will come up with a use for it. So in that kind of pure research kind of angle, I think that we don't really even know what the possibilities are. I mean, we're the pure research side. It's like we just want more stable clocks. We want high frequency. We want them to be able to run for longer. So in other words, like, a lot of optical clocks nowadays is just a laser table with a bunch of lasers and mirrors and,
right.
and it can run for 5 minutes or run for 24 hours or something, but it doesn't stay locked. It's too much fine tuning. So we got it to a point where like here, we know it's possible, but then commercial companies take that idea, they read our papers, we talk at conferences, they learn that it's possible. They figure out how to miniaturize it and sell it. And so once they can sell it, then people can actually use it. So in other words, like we have for some part in 10 to the 18th, stability that we can't get that out anywhere. Like there's no time.gov. There's no satellite. There's nothing that you can get that from even across the street, right? I guess across the street you could with an optical fiber, but you can't get that time out. But what we did is we proved the technology, and then a company can figure out how to make it smaller. And hopefully that stays running for a long time so that then you can have two really good clocks. So then if you have a really good clock, you can synchronize it in one place and just carry it to another place and take that synchronization and put it at the next place. And so it's hard for us to say how this is even going to be used, except for, more data, faster, more minute positioning, I guess, if the atomic clocks in space are better. In quantum computers, it started out by like having 10 atoms, kind of like having 10 transistors, right? Like
right.
You could build a radio with 10 transistors, but you can't build a computer. A computer's got a CPU. It's got like a billion or billions of transistors on it, billions of gates, right? So if transistors got smaller and smaller to where you could put a billion on a chip, what if you could put 10 billion or 100 billion, million billions on a chip? And so that if a single atom is a gate, that's the fastest, smallest gate you could have. And so there's no quantum computer that has a billion gates on it yet, but it's getting there, right? So if it does, then now you're talking about like processing, cryptography, solving, computers solving equations and stuff. So you could be able to encrypt massive amounts of digits and things like that. So at NIST, we have not really ever been too much in the business of figuring out what to do with the clocks. We just try to make better clocks.
Completely understandable. Out of curiosity, is there anything that you've learned over the course of your career about time that you found extremely interesting, or a fun fact, or a quirky little topic?
Man, it's so esoteric that everything about it's kind of quirky. And the
it's
fact
all relative.
It's relative. It's quirky, and you think about like what you know now, or say what someone knew 100 years ago about two things that happened at exactly the same time, right?
Right.
It was exactly the same time, and what they could measure it with in that era. Clocks get better, and we're like, oh, we actually know that this one happened before this one, right? So but these other ones are at the same exact time, but these other things we could measure. So then you find two other things that seemed like that they were exact same time 20 years ago. And now you can tell one happened before the other one. So that simultaneity, it means that you just need better clocks, and you can see that things aren't simultaneous. So is anything simultaneous? It just depends on what minute level you're talking about. So I think what I've kind of learned is that the closer you look at something, the less you know, almost, and that's the same. So if you want to take it on a grander scale, like about people, right? Like you meet someone for this first time, or you get to know them, and you're like, oh, okay, I kind of know that person. You spend a week with them, or you spend a year with them, or you get married, or you know someone for a long time. The more you know about someone, you realize you keep learning more and more things. And you're like, I feel like I know less about them now than I did when I first met them, because I know a lot more things, which means that there's a lot more things that I realize I don't know. So it's like that. So that metrology is like looking at things closer and closer to find out all the things that you don't know. And if you have the best clock in the world, how do you know, right? There's nothing to compare it to except something worse. And if it's something worse, then all you're measuring is how good the bad clock is. So you need a better clock to tell you how good your current clock is. And so that's relative in a different way, right? It's like So if you're going to characterize how good is the best clock, you have to characterize all of the things that you got to that stability. So you're looking at, temperature or solar radiation or black body radiation. You have to basically, to come up with the uncertainty analysis of some clock, you have to come up with the uncertainty, all of the uncertainties of all of the things you got to make that clock, and you come up with an uncertainty estimate. And so until you have better clocks, you don't know how good that clock was. So it's kind of like that, you submit data to the circular T for all the countries, but you don't know how good you were until you got, several weeks later, you got that result back of that international average. So okay, here's how good you were 3 weeks ago or 4 weeks ago, so I feel like if you have the really good clock, you can't tell how good it is. You can make another one. And if they're both at the same rate, it's repeatable, but you still don't know how good they really are until you come up with a better clock. And now you say, okay, well, now we know how good those clocks were. So I think that kind of relative nature of things and looking at things closer and closer, I think that's something that I've learned and gotten interested in. But I also, I did a blog post at New Year's coming from into 2023 to 2024. It's on the NIST blogs. And it's more about the relative, how our perception of time. And, if you have a really busy day, it might go by really fast. Or if you're just watching a pot boil, it might seem like it takes forever or whatever. Or if you're put in a dark room with no light, no sound, no external influences, you sit there, and if you said, okay, tell me when a minute's gone by, or tell me when 5 minutes have gone by, maybe someone would say after 20 seconds, they think a minute's gone by, or maybe after 4 minutes, they think a minute's gone by. We perceive of time based on all of these things happening around us or what we're doing. And so that's why time is so relative. Or like when you get older, an 80-year-old person thinks of a year as a really short time, whereas a 15-year-old person thinks of a year as like a really big, possibly. I mean, the theories are, that's the relative or the ratio of that 1 year in the 80-year-old's life is a small chunk. So that seems very fast to them, and because they've lived for 80 years. And so I kind of tried to delve into that a little and research just people's perceptions of time. So I think it's the psychology and the physics kind of coming together when it's something like time.
Now, as we're coming up, we're just over the hour for right now for recording. Is there anything that you would like to add or have listeners take away from this conversation?
I think leap seconds is a fun thing to talk about.
Okay, tell me more.
So imagine early timekeepers in like the ancient Sumerians, Mesopotamians. Remember I talked about the sun as a clock.
Yeah.
And the astronomers were like the super smart folks, right? They said, hey, look, we can tell where the stars are. And, the sun is up for less time, in this periodic, like if you see these things where the sun doesn't go all the way overhead, it goes over there. So it means like you're not on the equator. So the astronomers were seeing things that other people weren't seeing. And so they were the original timekeepers. They were the ones who were saying, look, things are cyclical and the earth is rotating on its own axis. The sun's not going around the earth. The earth is rotating. And so the sun goes by every time the earth rotates. But the earth precesses around the sun. So you have the seasons. So you start thinking about time and periodicity, not in 1 day, 1 minute, 1 hour, but in 1 year or multiple years. And so you're talking about like long term. But really what that all boils down to is Earth and its rotation is their clock, it's that original clock. It's that periodicity of the Earth rotating. And so you can count the days and years with Earth, right? But when clocks got better, they're like, oh, wait, we got to adjust the clocks because they're getting off from what the Earth is, right? But when you get even better clocks, like atomic clocks, you're like, the atomic clock doesn't care where Earth is. It's just going at its own stable thing. It's much more. So what you realize is the Earth is not a very good clock, even though it's been a clock for thousands of years or whatever, because you got a better clock. And so once we define time as based on atomic clocks, which happened with a treaty or an agreement in 1968, but it started in 1972, we said, okay, we're going to base the definition of a second based on atomic clocks. We're not going to move it when we find that Earth is changing, and we thought that clocks were changing, but it was really Earth changing. The Earth's axis is on a wobble, and then you have like something like an earthquake or whatever, and it wobbles, and the tides and things. Earth is not really that good of a clock, but we didn't know that until atomic clocks. And so now we said, okay, we're going to define time by atomic clocks, but we're going to keep that Earth time significant. So when Earth gets off by about around a half a second from our atomic clocks, which we know are more stable, we're going to adjust just the time of day by a second. So that's called a leap second. And so basically you add an extra second, kind of like leap day, where you add an extra day in the calendars, because unfortunately, when the Earth goes around the sun, it's not exactly 365 days. So you have to have leap days every so often. And so this leap second lets Earth catch back up, because the original definition of the second, the duration of the second, was kind of based on a long time's worth of data, 100 years of data. And so Earth was getting behind, but not behind at a steady rate. If it's the steady rate, it was just like, oh, we should change the definition. Some years you would have a leap second. Sometimes you wouldn't have a leap second for 2 years. And so that's Earth being inconsistent. And so when we get about a half second off, and this is based on long baseline interferometry, there's an agency called the International Earth Rotation Service. So they're astronomers with good clocks, right? So they say, here's how far Earth has gotten off. And when Earth is behind by about a half second, they say, let's do a leap second. Then that lets Earth catch up and get ahead by a half second. So then we were never off by more than 0.5 or 0.6 seconds, because we went from off by 0.5 or 6 to 0.4, 0.5. So that's just us trying to stay cool with the astronomers who are like, look, like Earth is the original clock. Like, don't leave us behind. And so since 1972, there's been an equivalent of 37 seconds. And so that's how far Earth's gotten off. Except Earth has changed its rate. And we haven't had a leap second since 2016. So Earth has actually caught up to us.
Yeah, we were speeding up.
Yeah. And so that rate has caught up. So now we're about at 0. But if it keeps speeding up, we're going to have to take away a leap second, what they call a negative leap second, because so instead of a leap second is an extra second. So you go like, instead of going 58, 59, 0 to the next minute, you go 58, 59, 60, then 0. If it's a negative leap second, because Earth is ahead, then you're going to have to go 58, 0, so like, and so far that's never happened. So any digital systems have a chip potential. Think of statistics, right? You're taking a data point every second. Now you have this 1 minute has 61 seconds in it. Like, it throws things off, or clocks that synchronize are going to freak out on their steering. And so like networks like Google or maybe eBay, there's other ones that they've decided, we're not doing this 1 second quantized second thing. We're going to distribute that second offset in 6 hours or 12 hours. So they actually changed frequency in all of the network synchronization. They changed frequency so that absorbs that second into, they're changing the frequency before and after. So they've kind of slid it in instead of this quantized second that can make a bunch of, data have problems or whatever. So a negative leap second's never been done. You guarantee that no systems are going to be able to handle that. That could be maybe catastrophic. I don't want to be an alarmist or anything, but they're talking about getting rid of the leap second, not just for that, but just for systems that statistically have to deal with it. And so we could just say, forget leap seconds. We're going to go on these atomic clock frequencies. And the IERS can still tell us how far Earth is off. And that's just going to get further and further off in one way or the other. It doesn't matter. but we don't have to change our time of day. You know, it's kind of like daylight saving time, right? Like everyone hates changing their clocks.
It's so minute
Yeah.
for some people that the leap second is almost trivial until it's a significant amount of time.
Yeah. But in the
Right?
case of networks, you're talking about bandwidth and data and all this stuff. As we were talking about, you need to divide that second by smaller and smaller. 1 second is a billion nanoseconds, right? So if you need nanoseconds, and here you are with like slamming a whole nother second or taking away a second, that's billion nanoseconds. Like that's huge for some people. You know, if we had to, if you got up in the morning, it's like, hey, everyone, set your clocks back by a second. That's not going to affect us, right? You might have been late to that meeting by 5 seconds, and now you're 6 seconds late or 4 seconds late. I mean, in our daily lives, we don't think of a second, but that hour, everyone doesn't like that hour. That's,
Nobody likes that hour.
That's, that's the jet lag of daylight saving time. So, but yeah, computers don't like that second offset. So they're talking about getting rid of the leap second. They've been talked about it for 20 years. So it's probably getting closer, but that's another one of those kind of fascinating things that you might see on the news and be like, what is this? So now you kind of know it's another thing that time throws a wrench in the works.
Absolutely. Now, anything else before we wrap up?
Man, I think we covered a lot of bases. Yeah.
So, Andrew, thank you for coming on Breaking Math Podcast. It's been a pleasure chatting with you about time. And for our listeners, you can follow us on our website at breakingmath.com, and also our Twitter or X, depending on what platform you like to call it, for Breaking Math Pod. And now we're also on Blue Sky for Breaking Math, just strictly Breaking Math. Thanks for joining us, folks.